Hello and welcome to Assignment 2. The main topic of Assignment 2 is the difference between burst and series mode. We will also investigate the difference between different sampling frequencies and different sampling numbers. We will understand how to use the RTC and event system to trigger ADC measurements, and we will also configure the Tiny2 to go to sleep between conversion to save power. We will start with burst mode. As you can see, the ADC init is almost identical to what it was in the previous task. The only difference is that we are no longer in free running mode, and we have added this bit here, ADC start event trigger, which means that the ADC conversions will now start on events instead of continuously running as it did in the previous task. If we go over to the main function, we will see that there are some more changes. The first to note is that there is no more ADC software starting, because we are now triggering it by events instead of by software. The second change that is worth noting is that we now have the RTC init and event system init. And if we first go to the RTC init, we will see that the RTC is simply set up, no prescaler, it's enabled, it uses the 32 kHz clock, and it has a period that is calculated using this macro, ADC result frequency. And this is a macro that we have created that we can use to automatically calculate what the period should be depending on what kind of frequency we go. So this macro exists in the header file. And we can see at the moment we have set the ADC result frequency to be 64 Hz. This means that on a frequency of 64 Hz, we will get a new result ready in the result register. In addition, to connect the RTC period, which creates the event, with the event system, we also have to initialize the event system. So we say that the event generator for channel 0 is the overflow event generated by the RTC. And we say that the ADC is a user of channel 0, which means that the ADC event system listens to events on channel 0, which will then come from the RTC, as the RTC is the peripheral generating events on channel 0. And that's it. So let's flash the device, start without debugging, and let's see how this looks in the data visualizer. So we once again have to load the configuration by pressing the load workspace. And this time we select assignment 2, open, OK. And then we have to start the UART communication. And then go to variables streamers and select the USART source. And then we see that the signals are showing up, and still, if I press the button, they will be bouncing up and down. And what we want to take the time now to look at is the effect of the number of samples. We zoom really close, we go to 0 to 15 on both of the signals. The red signal is just a single sample, while the green signal is the accumulated sample, which is an average of all the 1024 samples we are making. And as you can see, that just a single sample has quite a lot of noise on it, while the average signal is smooth and straight. There's no noise to be seen. And let's see what happens if we reduce the number of samples. So if we go back to the code and we go to the ADC header where we are setting the number of samples. So here we can see that the samples is 1024, but we can change that to say 8 samples. We flash the device. And if you now look, we see that sometimes we get these spikes. We are not able to average out as much of the noise this time because we're using fewer signals. So the conclusion is basically the more samples you have, the better your ability to suppress noises, the more of the noise you can average out. So let's look at the series example. We use series instead of burst. We also will configure the device to go to sleep between samples. So first, let's look at the changes that needs to be done to the ADC. So to change the mode from burst to series, we only need to do one simple thing. And that is change this one from ADC mode burst to ADC mode series. But we also need to do some additional changes to make the ADC work in sleep mode and to be able to wake up the device, because the idea now is that in between samples the device will go to sleep. But once the ADC has new results, it will wake up the device so we can read those values. And this means two things. First off, we have to activate the ADC in sleep mode, which is done by setting the ADC run standby bit. In addition, we have to enable the ADC ready interrupt. We also have to make the interrupt routine then, which handles the interrupt. And we have to do some slight changes to the ADC assault ready to work with this new interrupt routine we have created. In addition, to make the device go to sleep, we have to do some other configurations. So we have now created a new sleep control init, which sets up the ability for the device to go to sleep. So if we take a look at this one, we set the sleep to standby mode, which is the lowest mode sleep mode where the ADC can still run. And of course, we enable sleep mode. In addition, we have to enable global interrupts to make the ADC interrupt work so we can wake up from sleep. And in the while loop, we have to go to sleep. In addition, we have made some small changes to the transmit function. And that is, we have added this guard here to make sure that the USART communication is finished before the device goes to sleep. And lastly, we have made some small changes to the RTC init. So now instead of calculating the period on the result frequency, we will now do it on the sampling frequency. And the difference is, since we now are in series mode, one trigger from the RTC will trigger only one sample instead of an accumulated result as it did in the previous example. Which means that we now control the sampling frequency instead of the result frequency. So we have created this ADC sample frequency macro. And as it's easier to think in terms of result frequency than sampling frequency, we are calculating the sampling frequency based on the result frequency and the number of samples we are doing. So the result frequency is 64 Hz and the samples is 512. And it's important to note that the more samples we're doing, the lower result frequency we can have. So if we do 512 samples, the maximum result frequency we can have with the current RTC setup is 64 Hz. So let's look at how the signal is in the data visualizer. So start without debugging. And then we'll start running the data visualizer. And we can see that the signal is able to follow. So the green signal, which is the accumulated samples, is able to follow and represent the red signal, which is just a single sample, very well. But if we change the result frequency to something much lower, like 1 Hz, and then flash the device, and look at how this looks in the data visualizer. And now what I'm doing is I'm pressing the button very rapidly in a periodic fashion. And now if we look at how it looks, we see that the single sample is able to capture the rapid changes in the signal I'm creating by making this rapid pushing motion, while the accumulated signal just looks like the signal is constantly flat. And that is because our results are too slow and we are averaging away the changes, which means that if the result frequency is too low compared to the frequency of the signal we want to capture, we will lose information and not be able to recreate it properly. That's it for assignment 2. Thanks for tuning in.